In this video, we are going to solve systems of linear equations using TI-83 or 84, and also we are going to check the solutions of this system by graphing the system of equations. Here in this, let us take a system of equations in three variables x, y, and z. If that system of equations with the three variables x, y, z are drawn, the graph will give us three different planes, and if those three different planes meet at a single point, then that common point becomes the solution to the system. We may have a case when those three planes are parallel, or maybe two of them intersect. Any two may intersect, not all three intersect. So we do not have any point common to all three, in which case it has no solution. We may have a case when all three intersect and it has a common line. So when you have a common line, then you have got many points which are common to all those three. So it has got many solutions. Or you may have a situation when all those three planes, one lie above the other. That is, all three represent the same plane, in which case, again, you have got infinite number of solutions. We have already seen this algebraic method in my other videos. I have explained how to use the substitution method, elimination method, the matrix Gauss-Jordan method, elimination method, as well as the determinant method using Cramer's rule. Here we are going to graph and view the common point or the points which can be a line. And also we are going to use at TI-83 and 84 using that reduced row echelon form method. Now in order to get that rref, first we have to create a matrix using the coefficient of those matrix, the equations, as well as the constants what are given in that system. You can create the matrix by selecting second x inverse, which gives you the matrix. In that we can edit. We can edit that as a 3 by 4 matrix. If you have a system of three variables, then it will be 3 by 4. And then quit. Again you select the matrix math to select your reduced row echelon form of this particular matrix, whatever you have selected. That gives us an easy technique of solving the system of linear equations. Let's see how to get the graphical method and the TI-83 and 84 method here. Let's take this first example. We have a system of equations. In order to get the solution for this, first let us graph them. When we graph the system, we have got three different planes as shown in this diagram. And those three planes have a common point, a point A, which is common, and that point 1, 2, 3 becomes the solution to the system. For the same system, we can check whether that 1, 2, 3 is a solution by creating a matrix, a 3 by 4 matrix with those coefficients 3, 4, negative 1, 8, 5, negative 2, 1, 4, 2, negative 2, 1, 1. This is created using the coefficients of x, y, z and the constants which is on our right hand side. Select the reduced row echelon form of this matrix. That reduced row echelon form gives a matrix which is given as 1, 0, 0, 1, 0, 1, 0, 2, 0, 0, 1, 3, and the last column, because the first three gives us the unit matrix, and then the last column gives us the solution, that is x is 1, y is 2, and z is 3. So this is an easy method of solving any system of equation, even if I have a system of equation more than 3 variables, then this calculator method, the reduced row echelon form rref method, will be very helpful. In our second example, we have another system, and if we are trying to find the solution for this, again we are graphing it. When we graph these 3 planes, it looks like 2 of them are parallel, and we have another one which intersects the other 2, but we do not have anything common for all 3 together. So this system has no solution. The same system can be solved using our rref method. That is, create a matrix B which is 3 by 4 with the coefficient and the constant, and take the reduced row echelon form. Here the first 3 does not give a unit matrix, and again when we observe the last row of this rref of B, it gives me 0, 0, 0, 1, which means that 0 is equal to 1, which is absurd. 0 cannot be equal to 1. So we have a very big question mark that the last statement, that last row is not true, and hence it has no solution. Our third example has got a system here, and when we are graphing it, it looks like all those 3 planes are almost the same. They are one and the same. They lie above the other. They are one and the same. So it has got infinite number of solutions, because you have got infinite number of points common to those 3, and hence it has infinite number of solutions. We can also show this using that rref method by creating a matrix for this system with the coefficients and the constant. We get the reduced form as 1, 1, 1, 2, 0, 0, 0, 0, 0, 0, 0, 0. The last 2 rows are true because 0 is 0. And since it is true, we get infinite number of solutions for the system. In fact, when you see the last 2 rows as 0, 0, 0, 0, 0, if I'm taking a variable for z as t and y as s, those are real numbers, the absolute constants t and s, then your x will become 2 minus s minus t from the first row. Since you have 1x plus 1y plus 1z equal to t, 2, you can easily get the value for x. So by changing the values for s and t, you get infinite number of values for x, y, and z. And this is justified that this system has got infinite number of solutions. So in this video, we saw 2 different methods of solving systems of linear equations with 3 variables x, y, z. We used the graphical method by graphing the planes and checking the point of intersection. And also we used a graphing calculator and used the matrix rref and verified whether it has one solution, no solution, or many solutions. Hope this video was helpful. Thank you for watching.